Now that we've started talking about equilibrium, we need to shift our focus away from simply talking about solubility product systems. So the next system that we are going to talk about are acids and bases. And in preparation for getting deeper into understanding acids and bases, I'm going to take a few minutes and review some of our definitions for acids and bases. So we have three definitions for types of acids and bases. I'm probably only going to talk about two of them for a while, and we'll talk about the third if it becomes appropriate later. So our first definition for acids and bases is the Arrhenius definition. And this is the most limited, and you may or may not have talked about it very much. Because it's so limited, we don't spend very much time on it. In the Arrhenius definition, an acid familiarly donates protons, or H+, to solutions. So we notice that something is an acid because the concentration of the protons in solution, or H3O+, hydronium ion, increases. And our definition of the base in the Arrhenius definition is a material that increases the concentration of hydroxide ion into the solution. So an example of each of these acids and bases, I'm just going to mention a couple of really familiar ones. Hydrochloric acid, we know when we dissolve it into water, it dissolves and releases its protons and then chloride ion. And so both of these two, the cation, the anion, dissociate from each other when they get into the water. And so that would be an acid. And then one of our typical bases is sodium hydroxide. And we know that this too is a soluble ionic compound, and it dissociates into sodium ion on hydroxide ion. And so because it dissociates and gives up hydroxide ion into the solution, it is a base. And the Arrhenius definition is pretty consistent with our next definition that we're going to talk about in terms of acids. But the key about the Arrhenius bases is that this only describes strong bases. So a quick reminder for you that a strong acid dissociates fully. So all of its H+ go into solution. So HCl is an example of a strong acid. HNO3 is another one. And so these ones, they separate fully into their protons and their nitrates, or really those hydrogen ions actually associate with water molecules, making the hydronium ion. But I'm going to use them pretty interchangeably, which is typical. So strong bases also dissociate fully, and they always have a hydroxide. So our common ones like sodium hydroxide, potassium hydroxide, barium hydroxide. Any hydroxides that you see, if they are soluble at all, then they are a strong base. So it's pretty easy with the Arrhenius definition to identify those strong bases, and it's convenient for us to list all of those strong bases because, as I just said, I'll say it again, if it is a soluble hydroxide, then it is a strong base. Okay, so that's the Arrhenius definition. It describes protic acids, and it describes strong bases. So it is somewhat limited, and so more typically we end up talking about the Bronsted-Lowry definition of an acid and a base. And these expand mainly the definition of the bases. So in the Bronsted-Lowry definition, acids also donate protons to solution. and bases accept protons from the solution. So now this allows us to talk about both strong bases and weak bases. So the Bronsted-Lowry tends to be a bit of a stronger definition, and we're going to mainly stick with the Bronsted-Lowry definition for acids and bases. As you might have guessed from our definition of strong acids and strong bases, weak acids don't dissociate fully. And similarly, weak bases don't absorb all of the protons. So if we think about what that means, if we think about a system where we are not fully having a reaction go forward or in the reverse direction, this might start to make you think about equilibrium reactions, and I hope it does, because this is exactly what's going on. So if we think about a strong acid, and I'm just going to use SA as my abbreviation here, like hydrochloric acid, if we think about it interacting with water, we can write this as an equilibrium system, because we can write every single system as an equilibrium. But the K for this reaction is huge. I don't even think it's published. It's such a big number. It's probably like 10 to the 20th or something like that. Anyway, for shorthand, we just write K is much bigger than 1 to say that effectively no reactants remain. So that's a strong acid. And if we think about a weak acid in contrast, then we might choose something like acetic acid, which is in vinegar. So in this case now, we have the same structure of our reaction, that the acetic acid dissociates to make hydronium ion and acetate ion. And if you look up the K value for this reaction, you will find it is 1.8 times 10 to the minus 5. So if we think about these two K values, we can see that the K value for a strong acid is very large, meaning that we have no significant amount of reactants remaining after this reaction has allowed to approach equilibrium. And in contrast to that, a weak acid where the K is less than 1, we know that this equilibrium reaction then, this is a K, it's not a tiny, tiny K like some of those solubility products, 10 to the minus 18 or something like that, but 10 to the minus 5 is still not super huge, right? So if this is less than 1, it means that we are still mostly undissociated here. That we mostly have reactants. That the acetic acid mostly still holds on to its proton and doesn't dissociate it very successfully. So if we think about strong acids and weak acids, and we think about strong bases and weak bases, our understanding from equilibrium can help us with this. That anything that's strong, we remember that this K value is much bigger than 1, and this reaction goes forward and leaves almost no reactants remaining. If we have a weak acid, then it depends on the K, on how far this reaction goes forward. And if you look at a table of acids and bases, usually they're just put in terms of acids, then you can see that these values are going to vary pretty widely. This is an example table that lists quite a few different weak acids. And if we kind of scan down, we can see that the strongest of the weak acids are things like iodic acid that only have a little tiny bit, like just slightly smaller than 1. So this would be 0.16 or 0.059 for oxalic acid. And then you can go down to much, much smaller. So we have various acids here. If we think about hypochlorous acid, for example, 10 to the minus 8, and it can keep on going down to phosphoric acid. The third of the H's on the phosphoric acid is down here at 10 to the minus 13. So this is just a few examples of different weak acids. When we want to do some calculations using weak acids, we have to remember a few things. And one of those things is that when we have a weak acid, and this is true for any kind of acid, I'm just going to stick with acetic acid since it's familiar to us as a material. And it also doesn't have a super crazy long chemical formula that's hard to write, like some of them do. So one of the things that I want you to remember about any acid in its acid dissociation reaction, that's what we're looking at here. An acid dissociation reaction starts with an acid, reacts it with water, makes hydronium ion, and makes the weak conjugate base of that acid. Even things like hydrochloric acid have a conjugate base. It would be the chloride ion, but it's so not basic. I mean, it really does not want to accept an H+ in solution, and so we mostly don't even think about chloride ion as a base. But any kind of acid dissociation reaction has an acid, it has water, it has hydronium ion, and then it has a conjugate base. And we can take that same conjugate base and we can write a base hydrolysis reaction, showing the opposite direction of this reaction, showing how this acetate can also act like a base. So if it's acting like a base, it's going to accept a proton and it will accept it from the water, which makes the water turn into hydroxide ion, and then we reprotonate that acetic acid. So just like we had before, here's our base, here's our water, here's our hydroxide ion, and here's our conjugate acid. And this is a typical base hydrolysis reaction. And because each one of these are equilibrium reactions, they have an equilibrium constant. We will routinely, for an acid, see them label it as a Ka, and for a base, a Kb. But I want to emphasize here that the letters, the sub A and the sub B, this is basically a formality that anytime we write an equilibrium constant, we need to know for sure what that reaction is, period. So it's just shorthand, letting us know that the Ka is for the acid dissociation reaction, and the Kb is for the base hydrolysis reaction. So if we think about these two reactions together, we can see that they form a pair. They both involve the same acid and the same base, and so we should have some way of relating the Ka and the Kb to each other. If we looked in the table, so that Ka for the first reaction was 1.8 times 10 to the minus 5. So let's look at these two reactions together. Let's also look at their equilibrium constant expressions. So if we write the equilibrium constant expression for that first reaction, we know that it looks like this. And for the second reaction, it looks very similar. Okay, so before we go very much further, I want you to think about water for a little bit first. Okay, water forms the foundation of our ability to describe how acidic something is. This sounds funny, perhaps, if you don't, if you haven't thought about it, because water is neutral, right? But how do you describe how acidic something is? What's the first thing that you think of when somebody says, how acidic is this? How do you know if it's acidic or if it's basic? That first thing that you probably thought about was the pH. That we routinely talk about the pH of a system, and we define it as minus log of the hydronium ion concentration. And our routine general sense is that the pH of water, of pure water, is 7, and that the range is approximately from 0 to 14. But where do these numbers come from anyway? Well, these come from the fact that water is known to self-hydrolyze. So water can, we call it autoprotolysis. That means that you donate a proton to yourself, and really you donate it to another molecule of the same type as yourself. You don't, like take one off of yourself and then give it back to yourself. So the autoprotolysis of water is a special chemical equilibrium reaction, and we give it a KW just to, again, be really specific. But this reaction, this equilibrium constant expression, we remember that pure liquids don't end up in our equilibrium constant expression, so it's just the concentration of the hydronium times the concentration of the hydroxide. And this is 1.0 times 10 to the minus 14 at 25 degrees C. So if we think about this autoprotolysis of water, we can figure out what the concentration of the hydronium ion is, and therefore what the pH of the water is at 25 degrees C. We can just use our ice table. So if we think about our ice table here, initially we have all water, and then we have none of our hydronium ion or our hydroxide ion. So our change step is to go forward, and at equilibrium we would have equal parts of the hydronium and the hydroxide ion, which means that in our KW expression it's going to be x squared is equal to 1.0 times 10 to the minus 14. So you can see that our x is the same thing as our hydronium ion concentration and also our hydroxide ion concentration. And if we take the square root of this, we will get 1.0 times 10 to the minus 7. And these are concentration units, so this would be molarity. So this is why the pH of pure water is 7, because minus log of 10 to the minus 7 is 7. This is where our pH scale comes from, that we typically have 7 as our pH neutral, and then the range doesn't actually go from 0 to 14. It can actually be negative if you have a really concentrated, strong acid. Okay, now what can we do with this knowledge that the equilibrium expression for Kw is this hydronium ion concentration times the hydroxide ion concentration? Let's look back at our two reactions for the acetic acid. So the acid equation looked like this. And it had a Ka of 1.8 times 10 to the minus 5. an equilibrium constant expression that looked like H3O plus CH3 CO2 minus over CH3 CO2H. Now, the base hydrolysis reaction, looked like this and had a Kb of OH minus CH3CO2H and CH3CO2 minus. So if we look at these two reactions together and we think about them, we could add these two reactions together, and if we did, we can notice that this acetate would cancel out with this acetate, and this acetic acid would cancel out with this acetic acid, leaving us with the water reaction dissociating to make hydronium ion and hydroxide ion. And if we multiply the Ka times the Kb expressions, we also will notice that those same parts will cancel out, because these two reactions, the acid ionization reaction, or dissociation reaction, excuse me, and the base hydrolysis reaction, when it's for the same acid-base combination, they are just the reverse reactions for each other. And so the net is water. So mathematically, these will cancel out, and what's left is the equilibrium constant expression for water. So for each acid-base conjugate pair, Ka times Kb is equal to Kw. So that means that we can calculate Kb for the acetate by taking Kw and dividing it by the Ka value for the acetic acid. And if we do that, then we will get 5.6 times 10 to the minus 10. And this is the equilibrium constant expression specifically for this base hydrolysis reaction that we have right here. So we not only can use the Kw water autoprotolysis expression to define the pH scale, we can also use it here to help us calculate Kb values. And this is especially useful because most tables only show us the Ka values, and so we have to calculate the Kb values if we want to do any calculations with them. So this comes into play a lot when we start thinking about pH for different systems. Now, calculating the pH for a strong acid, this is simple because we know that the concentration of the acid is exactly the same as the concentration of the H3O+. It dissociates fully. So if I say that I have 0.05 molar HCl and I want to know what is the pH, then I simply calculate minus log of 0.085. And when I punch that into my calculator, I get 1.071. But when we calculate pH for a weak acid, this requires an ice table and the equilibrium constant expression. So let's practice this with acetic acid. We'll stick with the same concentration just so we can compare apples and apples. So we'll say, what is the pH of a 0.085 molar acetic acid solution in comparison? Since its Ka is 1.8 times 10 to the minus 5 instead of really large. So our process for calculating this is exactly the same as any time that we're going to use an ice table, which is that we start out with our equilibrium constant expression. We write out our initial amounts. We know that we have 0.085 molar acetic acid. We assume that it has not yet dissociated so that we have no acetate and H+. Our change is therefore going to be in the forward direction, so we're going to reduce the amount of acetic acid and increase the amount of acetate and hydronium ion. And at equilibrium, we will be somewhat short on acetic acid, but we will have increased the amount of acetate and H3O+. So now we are going to take our equilibrium constant expression, just as we have in our previous forays into equilibrium calculations. And we're going to plug in these numbers. So on the top, we're going to have x squared, and on the bottom, 0.085 minus x, and this will be equal to our Ka value. So we now need to do a little algebra. So we're going to go ahead and multiply this onto the other side. You'll have x squared is equal to 1.8 times 10 to the minus 5 multiplied by the quantity 0.085 minus x, and we will distribute these two portions. So we will get 1.53 times 10 to the minus 6 minus 1.8 times 10 to the minus 5x. And I'm going to rearrange this. X squared plus 1.8 times 10 to the minus 5x minus 1.53 times 10 to the minus 6 is equal to 0. And at this point, I can either use the quadratic equation and do this by hand, or I can use a solver function on my calculator or using Wolfram Alpha. I recommend that you get comfortable with the quadratic equation because there are going to be times where you have to do this by hand. And so if you remember, we're solving for x, which would be negative b plus or minus the square root of b squared minus 4ac all over 2a when we've written our form of the quadratic ax squared plus bx plus c is equal to 0. So if I plug these values in, 1.8 times 10 to the minus 5 plus or minus the square root 1.8 times 10 to the minus 5 quantity squared minus 4 times 1 times c, which is minus 1.53 times 10 to the minus 6 all over 2. So when I simplify this, I get minus 1.8 times 10 to the minus 5 plus or minus 0.00247. That's all of the stuff that was under the square root and then taking the square root divided by 2. So in order to have a realistic quantity, these are concentrations, right? We can't do the negative root. We need to stick with just the positive root. And so if we do that, we should get x is equal to 0.00123 molar. And this would be equal to my H3O plus, because that's what my ice table defined my x as. It's both the concentration of the hydronium, or excuse me, the hydronium ion and the acetate ion. So I am going to get a pH by taking minus log of 0.00123, since this is the amount of hydronium ion that I have present. and this will be 2.91, which compares as much higher than our 1.071 value for the strong acid, and that makes sense. We should not have as acidic a solution when we have a weak acid compared to a strong acid. So I hope that you pause this video and practice through solving this quadratic equation for the acetic acid. And let's go ahead and set up another practice problem. So we'll choose another weak acid. Let's go ahead and do formic acid, HCO2H. This is the stuff that ants have, which is the in their venom. So if they bite you, it burns. Most of the time they don't bite you. But anyway, ants that have acid, they will do this. Well, I guess I picked this. It wasn't really intentional. But anyway, its Ka is 1.8 times 10 to the minus 4 instead of 1.8 times 10 to the minus 5 in the previous problem. So go ahead and pause the video and go ahead and calculate pH. And this time we will do, we'll stick with 0.085 molar, just because then we'll have two different weak acids and a strong acid, and you can compare the pH for all three of them. CHCO2H. Okay, pause the video, go ahead and calculate the answer, and then unpause, and we'll share the answer together. And if you have any questions, you can let me know. All right, so hopefully you were able to calculate that the pH for the formic acid was 2.42. So formic acid is a little bit stronger than acetic acid, but it's still quite a bit weaker than hydrochloric acid.